let me dispel a common misconception about reactions, and that is that reactions are not instant, even when they are spontaneous. Just as a reminder, a spontaneous reaction is one where delta G, or the Gibbs free energy, is less than zero. And delta G, or the Gibbs free energy, is the difference in energy between the reactants and products in a chemical reaction, energy that could potentially be used to do work. I would recommend studying thermodynamics if you're unfamiliar with delta G, or Gibbs free energy. So again, reactions don't happen instantly. They have some speed or some rate at which they happen, and kinetics sort of seeks to explain how that happens. So we might say that the rate of a reaction is equal to the change in the number of moles or the pressure or the concentration or number of atoms that are reacting or being formed over the change in time. Again, this triangle delta it means change. And so for reactants, we would say the rate is negative. And that's because reactants are being consumed. And for products, we say that the rate is positive. And this is for some hypothetical reaction where we have some reactant going to some set of products or one product. So instead of writing all these words, oftentimes we will write the rate as some symbols. So again, for the reactants, the rate is negative, so we might say negative change in the amount of reactants over time, and that should be equal to the positive of the change in products over time, or the change in time, sorry. These are what we call average rates. And that's because they don't actually tell us what's happening at any given moment, they just tell us what's happening overall. So we might actually want to know what is happening at any given moment. So again, we can say that the rate is equal to, now this time I'm going to use some calculus notation. It's going to say d reactants over dt. This is negative, so we've gone from delta, this triangle, to d, and they both sort of mean the change. So we have for the rate of the consumption of reactants, negative dr over dt, and we'd substitute in whatever reactant we had in moles, pressure, concentration, number of atoms, etc., etc. And then we could also talk about the products. So for the products, it would be positive dp over dt. And again, this is the rate of formation of products. And so now we have the instantaneous rate. And these tell us at any random or exact moment what the rate you measure is. And then finally, let's talk about the units that we would find rates in. So as I said, the rate is expressed in the change in moles or pressure or concentration or number of atoms over time. So we might see molarity per second. We might see molarity times second to the -1. We could see the partial pressure of something per hour. Radioactive decay is often in disintegrations per second, which is the same as number of atoms per second. So there are a whole bunch of different units for the rate of a reaction, and it really just depends on how you want to measure it. You know, time, all forms of time are technically equivalent. We could go between hours to seconds to years if we wanted, and it just depends on the exact reaction that you're considering.